this week we are gonna go through on chapter 2, which is hydrologic processes. We are gonna define what is hydrologic processes. Then after that we will go through Reynolds transport theorem, which is very important in hydrologic processes, events or definitions. When we calculate water balance equation, we use continuity equation. As we know from our fluid mechanics class, we derive everything from Reynolds transport theorem. So it's gonna be again reminder for the fluid mechanics class, but then we are gonna jump to the hydrology classes. So how we are gonna define, how we are gonna draw our boundaries with using this Reynolds transport theorem. Let's define the hydrologic processes. It's a process that transforms the space-time distribution of water throughout the hydrologic cycle. So we have the hydrologic cycle, as you remember, or I'm gonna show you next slide, and then we are gonna distribute it with the space and time and the location, and then like the first day, second day, the time, you know, like at 3 a.m. or 3 p.m. at Izmir location. So how this hydrological cycle occurs, if there is precipitation or runoff or like infiltration, transpiration, so everything we are transform this process, hydrologic processes, into space and time distribution. As it is here, it is the hydrologic processes as we defined last slide. So there is precipitation, then it comes to the mountainous surfaces, okay, then there is surface flow, there is subsurface flow, there is infiltration, there is groundwater flow, and it goes through the ocean or sea or lake, whatever it is, the stationary location, right? Then after that it evaporates and it becomes in the atmospheric moisture. It stayed there. What we said, like if 15 kilometers above the atmosphere, from the above the ground is our study area, 1 kilometer below the surface is still is our study area. So it's gonna be groundwater to evaporation, water moisture, everything is considered as hydrologic cycle. Most of the hydrologic processes can be modeled using the three basic laws of physics, which are continuity equation, momentum equation, and energy equation, which we are gonna derive, as I stated at the beginning, with Reynolds transport theorem. Reynolds transport theorem provides a consistent mechanism which is needed to develop hydrologic models. It's also called general control volume model. When we develop the fluid properties, it's divided into two, which are extensive properties and intensive properties. What is extensive properties? Extensive properties is dependent on mass, like momentum or density. Momentum, we know that is mass multiplied by velocity, so it's depend of mass. The bigger mass, bigger momentum, right? And density is mass per volume of the object, right? So bigger volume, bigger mass, it means bigger density. So it depends on, like, it change with mass. On the other hand, intensive properties is independent of mass, which is size, shape, velocity, etc. So we know that these all properties is independent of mass because it doesn't have weight measures, or mass unit like kilogram, gram, or whatever, right? Shape is length, so it's meter, centimeter, or whatever the unit is. Velocity is meter per second or centimeter per hour, whatever it is, right? Kilometer per hour. So it's just length over time. There is no mass. So these properties is called intensive properties. According to Reynolds transport theorem, we if we consider extensive properties as capital B and intensive properties as beta, so we can formulate beta is equal to dB over dm, which is the derivative of extensive property with respect to mass. In another word, quantity of B per unit mass of the flowing fluid. So let's go through other slides, then we can explain better. Before going further, we need to remember Lagrangian and Eulerian approach. Lagrangian concept focuses of attention as on the moving fluid particle. So like we are following the path in Lagrangian approach. But in Eulerian concept, focus in on moving fluid within a fixed frame or reference. So we are making a fixed reference, fixed frame, or fixed control volume, and we are observing there. We are not moving with it. We are just fixing the control volume, and then we are seeing how much input and output. In fluid mechanics class, you already know that Eulerian concept is much more easier than Lagrangian concept, because the path of the fluid is too much random, and it's, especially in turbulent flow, is impossible to follow one fluid particle if there is not too much attention paid on it. That's why most of the time in fluid mechanics and in these hydrologic classes, we are considering the Eulerian concept. Reynolds transport theorem. In this Reynolds transport theorem uses also Eulerian concept. So it relates dB over dt, which is the B was extensive properties. So extensive properties, derivative of extensive properties with respect to time, to the external causes producing this change. Alright? So if we say this extensive properties changing by time is the component of 1 and is concluded component 1 plus component 2, which is component 1 is the time rate of change of extensive properties stored within the control volume. The component 2 is net outflow of external properties across the control surface. So the time change of external properties is equal to the rate of change of external properties stored within the control volume, the first one. The second one is outflow of external properties across the control surface. So one of them is volume, the other one external control surface. So altogether is giving us how much, like let's say external properties as a mass, like continuity equation. So the mass is changing by time. So it's decreasing the volume of water, like the accumulated water, or increasing. We are deciding this one according to how much stored water inside this control volume and how much runoff is going out from the control surface. When we add together, we are gonna get our water balance equation, right? So it's exactly the same thing, but in mathematical form. So let's derive this Reynolds transport theorem equation. So let's imagine there is a fluid in region 1 and 2, which is the control volume, at time t occupies regions 2 and 3 at time t plus delta t, which when the change of time is delta t, when before it was 1 and 2, right now it changed 2 to 3. Okay, so this fixed volume of water is moving with delta t. So when we think about if this volume is considered, the particle of fluid is considered as dV, which is infinitesimal particle volume, which is dV, and we know that the mass of this fluid is gonna be dm, right? Or mass of infinitesimal particle dm, which is density multiplied by dV, which is the volume of this infinitesimal volume. And also we know that dB extensive properties of infinitesimal extensive properties is multiplied by beta dm. We know that dm is rho dV, so it's gonna be beta rho dV. So this one is the just one infinitesimal units external properties. If we extend it to whole fluid volume, so we need to make an integral of volume integral, right? Volume integral. We need to make a volume integral to extend the whole, let's say, fluid flow, or this fixed control volume, or let's say if we are taking care of taking measurement of one specific point of river, one interval. So this is our control volume. So if you take just one infinitesimal derivation of this external particle, and if we make it in the whole volume, we are gonna have the whole extensive properties, which is depend on mass, like momentum or mass or energy, right? So we can calculate it with a control volume integral. Now let's write time rate of change of external properties B by the first principle of calculus. So we know that dB dt is the time rate of change of external properties, is equal to, from the first principle of calculus, which is limit, we are taking the limit of two states differences, right? So when we approach delta t 0, we can find the derivative of B with respect to time, which is at the first state is when is time t, the second state is time t plus delta t. So the final stage minus the first stage for region 2 plus the third region, which is the third region is time t plus delta t minus the first region subtraction, giving us the limit, the derivative of external properties. Before we go through this control volume approach, let's go to see schematically what it means. Then after that we can continue to this derivation. On those two schematic view, we see the region 1 at the left side and region 3 at the right side, which are the control surface, which is flow is going through at this stage from 1 and leave from the third region, right? In second region is only accumulation or losing, like it means the storage of the water. So we can consider the second part of this second region as a control volume approach, and region 1 and region 2 it can be considered as control surface approach. In control surface, as from our physics class, we know that V multiply dot product V dot del dA, which is V cosine theta dA, right? Which is cosine theta is smaller than 1 because is in minus side, which is inflow to the region. So for the outflow is going to be the positive sign, cosine theta is going to be the positive, which is bigger than 0. Same approach, V dot product dA is going to be V cosine theta. dA is going to give us the VdA dot product, which is for the control surface integral. So if we go back our derivation, right now let's look at the control volume. So we can see that in second region is the only the part of limit delta t goes to 0. 1 over delta t is multiplied by second region of external properties, which t plus delta t time minus t time is gonna give us d over dt triple integral of beta, which is intensive properties, rho, which is density, and del V, which is the infinitesimal volume element. So this is our Reynolds transport theorem's control volume approach. Now let's see what is the first and then the third region, which is control surface approach. We need to use it, right? As we explained previous slides. So limit delta t goes to 0, 1 over delta t, b external properties at region 3 at t plus delta t time can be represented by double integral beta rho VdA, and for the first region is gonna be minus double integral b rho v dot product dA. So if we add all together, the rate of change of external properties is d over dt triple integral of beta rho dv plus the third region double integral beta rho v dot dA plus the first region of beta rho v dot product dA. So the final version of this Reynolds transport theorem is the integral equation of Reynolds transport theorem is dB over dt is equal to d over dt triple integral beta rho dv plus double integral beta rho v dot dA. Because we third region and first region, we know that is gonna be explained as the minus, so we can do with the control surface altogether. So it's the closed version of this integral equation, Reynolds transport theorem. As the beginning of the class, we stated that we have 3 basic equations, which is very useful for hydrology, which are continuity equation, momentum equation, and energy equation. So right now we are going to derive continuity equation by help of Reynolds transport theorem. It can be 3 types, which are fluid volume, flow cross section and point within flow. In integral equation of continuity is with fluid volume. In continuity equation, our extensive properties is mass, because in continuity we are looking for how much mass is flowing or losing or gaining. That's why we are gonna take B is equal to M. We know that if we want to find the intensive properties, we need to take the derivative with respect to mass. If we take the derivative with respect to mass of mass, it's gonna be 1. So instead of beta, we are gonna write 1 in continuity equation. And we need to use another law, which is conservation of mass. It is dB over dt, which is mass with changing by time. Mass doesn't change with time, so we are just taking it 0. When we substitute the terms into the Reynolds transport theorem, in the left hand side dB dt, which is dm dt, is 0 because of conservation of law, is equal to dB over dt, the control volume integral, triple integral, rho beta is 1 is gone, so rho dV plus control surface integral rho v dA is our the final version of continuity equation. And in civil engineering we are always using water, which is incompressible fluid. So under the assumption of incompressible flow, we know that the density is not changing or is a function of any variable like x or t, space or time. So we can consider as a constant. So we can take it on the outside of the integral. Due to its the left hand side is 0, we can cancel it. So our final version of continuity equation in integral form is d over dt triple integral dv volume plus double integral v dA is gonna give us equal to 0, right? Okay, first term is volume of the fluid stored within control volume. In another expression is ds over dt, right? In water balance equation, ds over dt, the storage with respect to time. And then second term is volumetric flux across control surface. So VDA, we can say the outlet and inlet, especially the same thing as like third region and first region in the previous slides. Also, we can consider as the outflow minus inflow. Therefore, we come to conclusion for the continuity equation, which is ds over dt, the time of rate, the time of change of time of storage is equal to inflow minus outflow. If it is minus and positive, as we know, either we are losing or gaining the water. If the flow is steady, it means if the storage is steady, it doesn't change with time. That means our inflow and outflow, which is income to the control volume and outflow, outcome of the control volume, is same. This equation is valid for single phase flow, but in hydrology we mostly is very common multi-phase flow. what is multi-phase flow is if you have liquid like water plus moisture, or liquid plus the sediment transport, sediment inside, solid particles, snow with rain. Okay, so all this is multi-phase flows we are calling. For this case, we need to write continuity equation for each phase. As an example, if we have evaporation, we need to write liquid phase plus vapor phase. So if there is an let's say river, the sun comes on it and then it evaporates some water, right? So liquid phase plus vapor phase, the evaporation phase, you need to add each other. Then you will calculate it. Your inflow is equal to outflow. For example, again, for closed system, it can be written minus infinity to the infinity, take the integral with respect to time. The inflow is the same, minus infinity to the infinity time integral for outflow. As an example, you guys made this week for river water budget residence time calculation. When you do this one, you calculated what inflow and what outflow. You add it all together, the flow rate, runoff, right? Runoff, and you made it steady. So inflow and outflow is steady or average. You take the average and then you made it your calculation, but basically the same thing. You add the evaporation, you add the runoff, so you add the multi-phase, everything together to calculate how much the residence time in the river, one water particle. We see this continuity equation as a continuous time domain, as it's seen in the left graph. When you have continuous time domain, you will have this kind of equation, you can use it. But in reality, in the air stations, we have discrete continuity equation, like discrete data, right? Sample data representative, like at time 1 we measure the precipitation, the second time, third time, fourth time, like you have like every hour or every 2 hours, every 3 hours we have our precipitation amount or the water accumulation there. Then we are taking the measurement and we are going to apply it in order to find our continuity equation. Or we have again pulse data representation, so we are going to have an interval from like 1 hour. During this 1 hour the average of input is this much, or the second interval is a little bit above, like blah 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 blah. And we are gonna take the integral according to this impulse time, discrete time index, and we will find our discrete continuity equation. We are gonna solve an example. It will be explained better. It will be understood better. But it's just this graphs is just showing you normally we have discrete data, so we need to apply discrete continuity equation. Okay, let's solve one example about the time distribution of storage on a watershed calculated using the discrete time continuity equation. So we are gonna see here the incremental precipitation, instantaneous stream flow, like when these two is different each other. And when we solve the question, you will see it. We need to convert this instantaneous stream flow into incremental stream flow. Then after that we are gonna apply all this continuity equation. The question, the example is calculate the storage of water on a watershed as a function of time given the data in columns 3rd and 4th for incremental precipitation over the watershed and stream flow measured at the outlet. These data are adopted from a flood that occurred in Texas 1981. The watershed area is 7.03 miles square. Assume that the initial storage is 0. So let's jump to solving this question, and we can talk about later the conclusion. In this question, we have a table, the time distribution of storage table. In this table, it's given incremental precipitation and at column 4, instantaneous stream flow. Okay, let's close up right now this guy. Okay, what is the incremental and instantaneous? Incremental means during this 0 to 0.5. Okay, so in this duration, what is the precipitation? It's given the average value of precipitation. But when it's continuous, at that time 0, what is the stream flow of in this event? Okay, storm, in this storm. So at time 0.5 hour, like half an hour, 246 cubic feet per second. At an hour, okay, 1 hour, we have 283 cubic feet second. This is the instantaneous, is a point. But as we see, this incremental, it means like we have an, let's say we have an graph, and graph, if it shows like this or decreasing, whatever. Okay, so this is incremental. If you see here the precipitation, the rain between 0 to 0.5, it start to rain like 0.15 inch. Then after that it increase till 2.2 inch in half an hour duration. Then after that it start to decrease, and after 4th hour, when it start to beginning of the rain, it start to not accumulated water anymore. There is no rain till 8 hours. Okay, so this table shows from 0 to 8 hours duration of a catchment hydrological event. So we know here the precipitation, here the stream flow, which is outflow of the catchment area. So but this guy is incremental, this guy instantaneous. In order to go further, we need to convert this instantaneous event as incremental event. Okay, incremental table form. So in order to do this one, we have to convert this 203. Let's write it down here. Let's say Q at 0 is let me see, 203 cubic feet second. Q at 0.5 hour is 246 cubic feet second. Here. Okay. In order to do this incremental version, we have to find the average of these two. So it's going to be 203 plus 246 over 2. Is going to give us, let me see, it's going to give us 224.5 cubic feet second. Okay, 224 cubic feet second. What we need to do, we need to convert it to the inch. like this incremental precipitation, as you see here, this incremental precipitation's unit is inch, but stream flow unit is cubic feet per second, which is let's write here, cubic feet second is feet cube per second. So what we need to do, we need to multiply by time variation over area in order to find an inch, right? So we can convert feet to the inch. Okay, let's do it. We know that time is 0.5 hours, which is 30 minutes. So we can multiply this 224.8 cubic feet second. Sorry, it's not cubic feet. It's cubic feet second. It's not cubic feet per second. Sorry, it's cubic feet per second. So 224.5, right? We need to multiply by time, which is 30 minutes and 60 seconds, which is 1800 seconds. It's gonna be is equal to when we multiply 224.5 multiply 1800 is gonna be 4.4 multiply 10 to 10 to power 5 feet cube. Okay, 10 to power 5 feet cube. Then later, what we need to do from feet cube, we know the area. Area is 7.02 miles square, right? 7.3 miles square, which is we need to convert it to feet square. We need to multiply 7.03 multiply 5,280 is 1 mile is 5,280 feet. So it's square, so we need to make it square. Then we will have 1.96 multiplied by 10 to power 8 feet square. Okay, our area is 1.96 multiplied by 10 to 8 feet square. We know that here 4.04 times 10 to 5 feet cube. Then we can 4.04 multiplied by 10 to 5 feet cube over 1.96 times 10 to 8 feet square, which is the area. This is the stream flow over area, is gonna give us let me calculate 2.06 multiplied by 10 to minus 3 feet. If I converted this one to the inch, I need to multiply 12, right? 1 feet is 12 inch. So it's gonna be equal to, if I calculate 2.06 multiplied by 3, is like approximately 0.02 inch. So this stream, let's go back to our table. As you see, when we concentrate 246 cubic feet per second, stream flow is gonna be incremental version of 0.02 at 0.5 duration. All right, 0.02 Then if you apply the same thing for here 246 to 283, you are gonna end up 0.03, and then so on. You guys can go through this example and then you can make it all this incremental stream flow. Okay, in the second part, after we had converted all the stream flow instantaneous data to incremental stream flow data, right now we need to calculate our storage. So in order to find our storage, so let's say delta S is equal to inflow, which is precipitation here, minus outflow, which is our stream flow, right? Both of them is incremental data, so both of them is inch. Then we can directly go through our table as we see here. So let's say that at 0.5, right, 0.5 duration, we have input inflow as 0.5, which is our precipitation, 0.15 minus our stream flow, which is 0.02, which is in the storage is gonna be 0.13 inch. Okay, in this area 0.13 inch. If we want to calculate it to the catchment area volume of how much stored, we need to multiply by its area. So when we find here 0.13, then we can go through the second part, which is the precipitation is right now 0.26 and stream flow is 0.03, and we will see is 0.23 is positive. So the storage is positive, is gonna be positive as you can see in the table. And then later on, after 6 hours, right? After, let's see, in the 6 incremental, which is 3. The time 3, third hour, it start to be losing water, the storage losing water. When we see here the cumulative storage, this is incremental storage. How much is increase at time duration? But here is the cumulative storage. So like at that time, how much water inside? In order to do this one, to formulate it, let's just like reminder that is gonna be S final is S initial, which is here the S initial is 0 in our question, and delta S. So how much water accumulated from inflow minus outflow. Okay, so when we see here, as we can see here, at time 0 it was 0. There was no water at the beginning of the storm. Then after that we can see 13. Then after that is gonna add 0.23. So total of 0.36 inch height of water. Then it's adding 1.27, which is 1.62. Then it increase. Then after that we are started to lose water till at the end 0.86, when it is the 8 hour, right? We still have water inside this storage. It still keep losing the water, but in our question we stop here at 0.86. So that means like when you design a drainage, when it's rain, you are gonna see like the rain, it comes directly, the storage is gonna be full, there is gonna be a ponding, then after that it's slowly decreasing. Sometimes it's so much decreased, so the ponding stay there like 2-3 days, and it costs of course the highway damage,
damage, highway damage, and or mosquitoes breeding, blah blah. There are too many disadvantages of ponding of water on the roads and on the surface of the grounds. All right.
As a graphical reading of this table, which is the result table, as we calculated, as it is given precipitation input as an incremental. We can read it, right? It finished at like where it's like 3 hour 3 or something, right? Or 2.5. And then after that we know that there is a stream flow output Qj. It's given from 0 to 0, and then it's jump till the end, 8 hours. It was given on as an instantaneous output, but we converted to incremental output, and then we just substitute into this graph. When we subtract each other, we can find it directly, the change in storage. So how much till 2.5 to 2.5 hours the storage is gained, then after that it starts to lose, right? Like we saw in the table. Let's just jump to not change the cumulative of storage. When we grab the change in storage and bring here, we can just see when the gain and loss intersection, we have the maximum storage on the watershed. So we will just add each other, then we will find the cumulative depth of water with unit inch with the dot points. When we gather together, like when we draw connect the dots, we will have instantaneous point of data at that, especially this storage on the watershed. All right, like so all the table we can describe it with the graph. So our question is done over here. When we go through momentum equation, we need to change our external properties. Instead of mass, right now we are going to use momentum, which is mass multiplied velocity. And when we calculate our intensive properties, we need to take the derivative with respect to mass, which is given just velocity. When we apply Newton's second law, we know that the time rate of change of momentum is equal to the net force applied in a given direction. So when we say dB dt, which is dmv dt, when we take the velocity derivative with respect to time, we know that is an acceleration. When you multiply by m, which is mass, is given us the force, which is total force, right? When we substitute into the Reynolds transport theorem, results in the total force, which is dB dt. Total force is equal to d over dt triple integral the intensive properties v, velocity, rho dv, plus double integral velocity multiplied by density multiplied by dot product of velocity and area. The previous equation is for unsteady and non-uniform flow. Unsteady, what we explained before, it is the time is not constant. Time is changing. Non-uniform flow, it means one in which the velocity does vary in space. So when x or y and z change, the velocity change. This is non-uniform flow. If it is uniform, it doesn't change with space, so it's constant velocity. So let's make one assumption that the flow is steady but non-uniform. Then our momentum equation turns to total net force is equal to only control surface integral, which is velocity, density, and velocity and area dot product. If we say if we consider that it is steady and uniform flow, then we are gonna say the velocity does not change with x and y and z, whatever, okay, with the space. So that means our total net force is equal to 0, so it's gonna be in equilibrium. The total force applied on this system is 0. And the last equation is energy equation. In civil engineering, we are not using too much energy equation, but in hydrology, it's beneficial to take a look on it. The extensive properties of energy equation can be taken as capital E, and this E is the amount of energy in the fluid system, which is the sum of internal energy, kinetic energy, and potential energy. And we know that kinetic energy is 1/2 mv square and potential energy mgz. And we can summarize it, B is equal to internal energy EU plus 1/2 mv square plus mgz. When we go through the internal properties, which is we need to take the derivative with respect to mass, which can be shown representative EU, the small letter of E, substitute internal energy per unit mass plus 1/2 v square plus gz. As I said before, as a civil engineer, you guys didn't take thermodynamics, but in the physics class you may see the first law of thermodynamics, which is if we have the change of rate of energy is basically equal to the rate of heat is transferred into the fluid, and substitute the rate at which the fluid does work on its surroundings. So dE over dt is equal to basically dH over dt minus dW over dt. dH over dt is as I said, the heat transferred into the fluid. Like for example, the sun gives heat to the ocean, lakes, sea, river, and makes some movement or stuff, and the fluid does work on its surroundings, movement or like work, you know. It's gonna be explained by the examples, so it's gonna be understanding more deeply. So when we substitute all together into the Reynolds transport theorem, we can get dH over dt minus dW over dt, the rate of change of heat minus rate of change of work, is equal to d over dt triple integral of the intensive properties, which is EU plus 1/2 v square plus gz, rho dv plus double integral of internal properties rho v dot dA, This is the energy balance equation for an unsteady variable density flow, which is a more complex form of energy equation. For heat, energy transport takes place in three ways: conduction, convection, and radiation. As I said, momentum and continuity equations are used at most, and energy equation is ignored most of the cases for civil engineer. However, energy equation takes an important part in hydrology for heating this hydrological cycle. And this is the last slide. It shows the radiation and heat balance in the atmosphere and at the Earth's surface. As you see in the graph, in the picture, incoming solar radiation from the space is coming. Let's say it's 100%. First, it begs the scattering by air and clouds, and from the surface, it didn't even take it into account. So it's almost like 6, 20, and 4%, which is 30% total of short wave. It directly go back to space again, and it stored 16% of this solar radiation absorbed by water vapor, dust, and ozone, and 3% by the clouds, and 51% ocean and land. Then this 51% of ocean and land surface absorbed solar radiation is go back to space again by net surface emission of long wave radiation, sensible heat flux, and latent heat flux, which is we are gonna see all these later on. If we need, we are gonna depict what it is. Okay. So basically just one thing here, maybe it wasn't understood. Latent heat flux. Latent, it means when the water change its phase. For example, from the water to the moisture, or water to the water vapor. So it needs latent heat. So this is 23%. Again, when we see the long wave at the upper side is gonna be again 70%. Like all is gonna go again back to the space, all the radiation. This is the, of course, perfect balance, but there may be due to the global warming and blah blah. So there is there is some kind the solar radiation couldn't reflected by the air or by the clouds. That's why there is more heat stored in the atmosphere, and then our global warming is increasing day by day. We come to conclusion. Today we are done for this week. We learned how can we derive continuity, momentum, and energy equation by Reynolds transport theorem. After this point, we are ready to go through the precipitation, evaporation, transpiration, and this subsurface flow, surface flow, all these hydrological cycles. Then after that, we are gonna concentrate on statistical approach of hydrology.